Okay, so good morning, everyone. Today we have Nils here with us. So Nils completed his PhD last year in Berlin, and after that he joined the Condensed Matter and Statistical Physics group at ICTP Trieste in Italy. And he works with exotic phases of matter, and such as quantum spin liquids and fractonic states. So Nils is visiting us, and it's a pleasure to have him here, and in particular today giving a talk about his research. So Nils, thank you for being here, and the stage is yours.
Yeah, thanks for the nice introduction, and also thanks, of course, for the invitation to stay here in Natal. I've had a great stay at IIP. So, as already mentioned, I'm going to talk about quantum spin liquids, but I've been told that since this is a more general seminar, I try to keep things very much at the basic level, so this is also supposed to be a bit of an introduction to the topic, so feel free to interrupt at any point and ask questions if anything should be unclear. So before I get started, also I want to thank my collaborators who are working with me on this project. So this is actually an older project that has been taking quite some time, but we're close to publishing it, and it's done together with my former PhD supervisor, Johannes Reuter from Berlin, as well as Yannick Schaden and Mikko Deepa, who's actually now also in Trieste at CISA, but started at IIT Madras when this project began. Okay, so for those of you who are not familiar with quantum magnets, I tried to summarize the main properties that you can expect in such a system. And of course, the very simplest cases are well described by spins being classical vectors which are interacting in some manner. And especially at high temperature, the thermal fluctuations will just lead to some very random arrangements of the spins. And these kind of phases of matter can be described very well using just classical statistical mechanics. So even in those cases, there can be some interesting properties. However, one thing that people usually expect is if you cool down these kind of classical paramagnets to some low temperature, typically the spins will form some kind of order. So this could be a ferromagnet. It could also be a more complicated kind of magnetic order. Or even something slightly more exotic like a valence bond crystal, which actually does not break any spin rotational symmetry because the spins form these entangled singlet pairs here. However, there's still a broken symmetry, namely in this case rotational or translational symmetry. Nonetheless, either of these phases of matter are similar in the sense that they can be described by so-called local order parameters. So these are just operators whose expectation value tell you whether you're in the ordered phase or in the disordered phase. Now, the study of quantum spin liquids goes beyond this kind of paradigm because we consider systems which do not exhibit any kind of local order parameter, and instead the ground state is given by a very massive superposition of all these possible configurations. And this can give rise to some exotic properties and some special particles that I also want to be talking about today. And more interestingly, the description of these quantum spin liquids is done via emergent gauge theories. So in the first introductory part of this talk, I actually want to introduce you to this concept of emergence and then finally also gauge theories themselves. And to do that, I will draw an example that is actually quite famous called quantum spin ice. So this is a particular type of a quantum spin liquid. And then later we will see how we can learn from this example by considering so-called gapless Fracton phases. And for the experts in the audience, I also want to briefly point out that there are also other types of Fracton liquids, so-called Fracton topological ordered phases. But these ones are gapped, unlike the spin liquids that I will be talking about today. Now, as promised, I want to keep it simple, so I decided to give a somewhat amusing example of how you can explain emergence. And I will, for now, leave the realm of physics and I will talk about football instead. So, a very nice example of how emergence work is if we consider a very historical match that actually happened not too far from here in Natal between two teams, Barbados and Grenada, in the 1994 Caribbean Cup. And as you can read here on the Wikipedia page, it actually led to a situation in which both teams attempted to score own goals. So this, in a sense, is an emergent property because it was done by a minuscule rule change. So how did something like this happen? The only change in rules that was done to the game was actually to include a golden goal rule. So if the match is undecided by the 19 minutes mark, something very common happens is that the game will be extended by another 15 minutes. However, the organizers of the tournament decided that it would be more fun if in this extension time any goal counts twice. And this sounds very reasonable, very innocent. You could not, or at least I could not expect how this would lead to such an outcome. So we need a little bit more context. At the start of this match, the tournament standings were as follows. Grenada was leading with 3 points, and Barbados was at the bottom of the table with 0 points. So if they do manage to win this game, they will be tied with Grenada. However, in this case of a tie, the goal difference is actually the quantity that decides which team gets to advance to the next stage. So Barbados actually needs to win with at least 2 goals with respect to their opposing team. And as it happened in minute 83, the standing was 2-1 for Barbados, so they were winning. But if the game continues without an additional goal, they will win the game but lose the tournament. And as time drew to an end, they decided to go for a desperate move, which is to force extra time by scoring an own goal. But the craziness does not even end here, because it happened that Grenada caught up to this plan, because the idea is that once the game goes to an extension, the golden goal will count twice. So if Barbados manages to go to the extension, they only need to score another additional goal, and they will have 15 minutes extra time to do so. So this is now the emergent property in this kind of system that led to a that came from a microscopic rule and completely changed the game of football. And in this case, Grenada actually had to attack both goals, and Barbados had to defend both of them. So now we are going back to the realm of physics, and I will explain now the second part of what an emergent gauge theory is, namely the gauge theory part. And again, I will start with something simple that you're all familiar with. This is just classical electrodynamics. It is a gauge theory, so in this case, you have an electric field which is satisfying the so-called Gauss law. So the divergence of this electric field gives you the charges in the theory. And the charges are well-defined, conserved quantities, and as a result, the only excitations that you can make in a system at lowest order is to add a dipole moment to the system. And of course, as you might know, charges in this classical electrodynamics are completely mobile. So if you want to move a charge sitting at some position here, all you need to do is to add a dipole moment to the system, and this will lead to a cancellation of these 2 charges, and then this charge will have effectively moved, and you can do this in any direction that you like. Now, I want to go to something more exotic ultimately in my talk, which is a so-called rank 2 U1 gauge theory, and it has a lot of similarities, but some crucial differences. And now we want our electric field to be a rank 2 tensor. So this sounds very artificial at first, but we will get there. And the new Gauss law is now taking 2 derivatives of this electric field tensor, and it again defines charges which are conserved. However, one thing that is different now is that not only are the charges conserved, but also the dipole moments. So the lowest excitation that you can make in the system is a quadrupole. And this now leads to some very interesting properties for the charges, namely that there's no longer any local operation that you can make to move them. So they are completely immobile. And these kinds of particles, which are mobile, have been studied in the past under different in different models, but they got the name fractons. And in this kind of gauge theory description, you can also have mobile charges, mobile quasi-particles actually, which are given by dipole moments of 2 charges. So if we form a bound state of a plus and a minus charge here, you can move this dipole in a direction perpendicular to its dipole moment by acting on it with a quadrupole moment, and then the same thing happens as before. These 2 charges can cancel out, and the dipole will have moved. But since they can only move along one dimension, not both of the dimensions, these are also special particles, and they have been known under the names of linons. So this looks very artificial, and it's not clear how to get something like that in nature, for instance, in a spin model. And we will now proceed to this introduction to spin liquids and how you can get emergent gauge theories using quantum spin ice. So we start actually with a classical model. It's an Ising model, so we have spins which are sitting on the corners of these tetrahedra here, and we start with a very reasonable Hamiltonian, which is just nearest neighbor interactions. But you can verify that if you take the sum of all the spins on one tetrahedron and you square it, you get something like this. And as it turns out, these two Hamiltonians here are exactly equivalent up until some irrelevant constant that does not matter for our consideration here. But this description of the Hamiltonian is actually rather nice because we can immediately read off the ground states that minimize the energy. So if we want to minimize the Hamiltonian, we only need to find configurations in which the sum of all the spins inside a tetrahedron adds up to 0. And this kind of ground state rule is usually known as an ice rule, and as people have figured out, it is actually equivalent to a discrete form of Gauss's law. And in hand-wavy terms, you can think of it as follows by making a local change of basis. So you still have Ising degrees of freedom, but now they can point either inside or outside of the tetrahedra. And in this case, this ice rule is equivalent to having a 2-in, 2-out kind of arrangement. So in this, if we identify the direction of spins as the direction of an electric field, you see that this electric field actually has no sources and no drains. So this is in particular a charge-free version of Gauss's law. Now, this already looks a lot like electrodynamics, but we can actually do this analogy further by considering excitations in the system, because if I flip a single spin, we have now created a pair of two charges, and these are completely fractionalized in the sense that they can freely move around in the system. So if I consider flipping this additional spin, the constraint in this initial tetrahedron here has been restored, and now this constraint here is violated and the charge will have effectively moved. So this is equivalent to this picture of adding dipole moments that I've shown you before. And you can do something interesting, which is to just freely move around this charge without any extra additional cost. And finally, if you close this loop, the charges can recombine and you're once again in a ground state that satisfies all the constraints with the additional property that now all the spins along this path have been flipped. So this is also an easy way to identify that the degeneracy of these ground states is actually extensive. And whenever you have a extensive degeneracy with an emergent Gauss law, a nice property is that you can see this in the so-called spin structure factor. So this is a very simple observable that is given by the spin-spin correlation function. It can be measured experimentally. It can also be easily computed. And you can verify whether the system has an emergent Gauss's law by finding these so-called pinch point features in the spin structure factor. So this is some kind of non-analyticity. And what is interesting is that if you increase the temperature in the system and you excite charges, then this non-analyticity will be lifted and the pinch point will broaden. Of course, when this degeneracy is so large, we expect quantum effects to play an important role. So a natural Hamiltonian to study instead is a model in which you not only have this perfect Ising anisotropy, but you also have some terms which can flip the spins and lead to some sort of quantum behavior. And in this case, we can do degenerate perturbation theory on this extensive ground state manifold in the same way that you do in elementary quantum mechanics. And you only need to identify the lowest order which tunnels from one degenerate state to another one. And this is actually exactly this loop move that I've shown you in the previous slide. And after identifying this process, you only need to write down an effective Hamiltonian, which sums over all these hexagonal loops in the system, and it flips the spins from a clockwise fashion to a counterclockwise fashion. And of course, the other way around. And this Hamiltonian is actually hard to solve. So a trick that people have borrowed from quantum Daimer models is to add this additional term here, which is proportional to mu, and all that it does is that it adds an energetic punishment to configurations that have a lot of flippable plaquettes, and this competition between these two kinetic and potential energy terms can be used to find a point, namely at mu equals 1 and v equals -1, and in this case the wave function that of the ground state wave function of this Hamiltonian here forms an equal weight superposition of all the possible ice configurations. So this is an extensively massive superposition, and it already looks a lot like a spin liquid, but as I told you before, a quantum spin liquid is characterized by an emergent gauge theory, so we also want to see how this quantum gauge theory looks like. And if you want to generalize the classical electrodynamics to some quantum electrodynamics, you need some non-commuting operators. So you introduce this vector potential here, and you express the S plus and S minus operators through this emergent vector potential. And this allows you also to define a magnetic field, which is some lattice curl of this vector potential here. And finally, if you do all these things, you can rewrite this Hamiltonian as a sum over cosines. And if you expand this cosine to quadratic order, there are some subtleties that I'm leaving out here. But if the fluctuations of the magnetic field are small, you can do this. And in this case, you arrive at a quadratic Hamiltonian, which you can solve exactly, and it leads to photon excitations. So the fluctuations of the electric and the emergent magnetic fields lead to excitations of gapless photons. We also have the electric monopoles, of course, still. So these are the classical charges that I showed you before. And there are some even more special particles here, the so-called magnetic monopoles, or also called visons, that I do not want to focus on here. What I instead want to point out is that just as in the case of classical spin ice, we have again a feature that tells us whether we realize this quantum spin liquid phase, and namely the structure factor of this classical spin ice gets modified by the photon dispersion. So these two quantities become multiplied together, and those give us the new spin-spin correlation function. And the pinch points are now suppressed proportional to this photon dispersion. So to summarize this first part, quantum spin ice realizes a so-called quantum U1 spin liquid. So this is a theory which is described by an emergent gauge theory of quantum electrodynamics. Now, the next step is to generalize this kind of idea to find these exotic Fracton theories that I introduced you to before. And the first step, again, is to start with some kind of classical gauge theory. I should mention some work that has been done by different people on this in the past, the so-called honeycomb snowflake model, which also realizes something like this. However, if we want to study quantum fluctuations, we are faced with the challenge that this model features some very complicated interactions, which are relatively long-ranged. And as of now, I'm not aware of anyone who has managed to study quantum fluctuations in this Hamiltonian. So instead, we want to simplify our tasks a little bit by constructing an even simpler model which has classical fractons. And the way to do that is actually to switch it around. So before we started with the spin model and then coarse-grained it to derive an emergent gauge theory. But now we want to start with a gauge theory that we actually want to realize, and we discretize it in order to obtain our lattice model. So as I've shown you before, the gauge theory that we are now interested in is a tensor gauge theory. And to simplify our lives, we work now in 2 dimensions. So this electric field is a 2x2 matrix. And to simplify our lives even further, we require it to be traceless and symmetric. So there are only 2 independent components of this electric field. Now we can simply expand this summation here and discretize derivatives using standard rules of discrete derivatives. And finally, we only need to identify the electric field components with some spin degrees of freedom, which are sitting on the lattice sides. Since there are 2 electric field components, we need 2 sides per unit cell. So these are the crossed and the non-crossed sides that I'm showing you here. And if you do all of these things, you arrive at a nice and simple looking discrete form of this higher rank H theory, now expressed in terms of spin operators. So to make it a bit more explicit, we want a model which in the ground state satisfies a rule where all the spins next to this plaquette with a cross in the middle added up with these sign structures here add up to 0. And if they add up to something non-zero, this would correspond to a Fracton excitation at this point. And the way to get an interacting spin model from this kind of ground set constraint is actually rather easy. We just need to learn from spin ice, and we perform a sum over all these plaquettes in the system and square this constraint, which will give us an interacting two-body Hamiltonian that actually realizes this Fracton physics in the ground state. And now you can also see where the spiderweb model derives its name from, because if you expand this square here, this leads to this nice spiderweb pattern of interactions. And okay, the first order approximation that you can make to try to solve this model is to do the so-called Gaussian approximation, which treats spins as continuous variables. So instead of having only spin up and spin down moments, you allow spins to take any value between plus and minus infinity. And in this case, you can immediately see that the ground state degeneracy is extensive, because we only need to satisfy a constraint for every second spin, but we have so for n spins we have n half constraints. So there's a degeneracy of the ground state. And what is also exciting is that we again have a feature in the spin structure factor that we can use to diagnose these kinds of phases. And this is a so-called fourfold pinch point. So this is again a non-analyticity in the structure factor, which now has this fourfold rotational symmetry. However, this approximation looks very crude, and indeed it is, because the relevant physical spins only have 2 degrees of freedom. So we need to find the way to solve this Ising Hamiltonian, and this is actually the first quite challenging problem due to this immobility of fractons. So if you want to do something like a Monte Carlo simulation, you start with a high temperature state and you try to cool the system down to a state which has no fractons. You run into the issue that the fractons do not thermalize well. They need to recombine in some way, but since they're immobile, they cannot find each other and recombine. This leads to very glassy dynamics. There are some workarounds that introduce loop moves in these kind of classical Monte Carlo simulations done by Benedict Placke. However, since I'm interested in the zero temperature properties, I want to do something rather simpler, which is to just try to sample stochastically from the manifold of states which satisfy this ground state constraint. So these are some configurations that you can generate randomly. I'm showing here white spins as spin up and black spins as spin down. And by naked eye, these configurations look very random, but there is a pattern to this randomness, which you can see by computing this spin structure factor. And this looks very much like the Gaussian approximation here. It has these nice fourfold pinch points. So this is a very good sign that in the classical case already for Ising spins, you realize these kinds of quantum spin liquids. So just for comparison, this is the structure factor that you would have expected from the Gaussian approximation for infinite system sizes. And the agreement for finite system sizes is actually quite nice. We can also now take a look at these kind of exotic particles that we get in this theory by starting with a ferromagnetic configuration. So this is something that satisfies this ground state constraint everywhere. And if we flip a single spin, we now violate the constraint in these 4 neighboring plaquettes. And this will create 4 charges in the system, and these are our fractons. We can also now consider a line-on by taking a spin on a boundary, or let's say we have a spin that is infinitely far away. We flip the spin here at the boundary, then we only get 2 of these fractons. And now we can take additional spin flips, which again create such a quadrupole moment here with these 2 ones canceling out. And this way we can move this particle around a one-dimensional manifold in exactly the same way that people have tried to realize in these higher rank gauge theories. And finally, using this kind of description, we can also understand why individual fractons are immobile, because if you continue this pattern here, you will find that there's a single charge sitting at the corner of this domain wall. So now the only way to actually move this charge would be to either excite even more fractons or to rearrange this entire domain wall, which is a highly non-local operation. So in this kind of theory, the fractons will be completely immobile. Okay, so now the work has been done on the classical model. Now the stage is set to study quantum fluctuations. But if there are any questions about the classical model, please interrupt me and ask a question. Yeah? Mm-hmm. Oh, sorry. This is the wrong direction. Which slide? Mm-hmm. Yeah. Mm-hmm. Yes. Okay. This is because I actually skipped some work that I had to do here. But if you are interested, the way to do it is actually to treat this kind of constraint here as a linear system of equations. So essentially, in the let's say you have a continuum description. This basically you can summarize as a linear system of equations, and the only thing that is actually hard is to find solutions that satisfy this up or down constraint. So in the field of mathematical optimization, these problems are actually very well known. So yeah, exactly. So what I did in practice is actually to take let's say an empty spin configuration. I flip some, I initialize some of these spins by random values, which basically restricts my solution space. And then I have a puzzle which is to find solutions that satisfy this constraint everywhere with these variables already fixed. And for that, I use a solver for these for integer programming. So essentially, there are numerics that basically brute force this. So this is of course an NP-hard problem, but as it turns out, because these types of problems are actually very dear to people, so people have put in a lot of effort of finding good algorithms for this. You can do this for reasonably large system sizes. But no, I cannot, yeah, exactly. So the number of ground states is extensive, so there's no way to find all of them for large system sizes. But the crucial task is to find a way to sample with an equal probability from all of these states. So if you want to not introduce a bias, this is why you have to actually include this first step of fixing some spins initially. So in the optimal case, you constrain your system enough that there's only a single solution or none at all. And in this case, you will have a sampling process which is uniform across this solution space. Yeah, so it's actually not super easy, but yeah, I glossed over the details there. Oops. Okay, so as I already mentioned, we want to study now quantum fluctuations in the system. And to do that, we again borrow knowledge from quantum spin ice. So we want to identify this lowest order process that goes from one fracton-free configuration to another one. And as you can work out for the spiderweb model, this involves an 8 spin flip term. So this is something that, for instance, would again arise perturbatively if you just consider single spin flip processes. And in terms of spin 1/2 moments, this operator takes a cluster of 8 spins around a plaquette that has the following shape. So this down, down, up, up, down, down, up, up. And then it flips them around to the opposite orientation. So we can once again write down an effective Hamiltonian that has this this plaquette flip term and this Roxer-Kivison potential. And to make it a bit more explicit, I'm again showing you a random spin configuration, and I'm highlighting all the clusters which can be flipped by putting a red dot in the middle. And as you see here, there's actually not very many states that you can tunnel into in this way. So these clusters are very sparse in the system. I mean, of course, one way to use this is to show that there must be an extensive ground state degeneracy, but it's also very clear that you cannot tunnel from every ground state onto every other ground state in this way. And in particular, this sector that I'm showing you here has very trivial quantum dynamics because none of these plaquettes are actually overlapping. So you can simply write down a solution which is a superposition of these plaquettes, but this will be a very trivial solution and will need to know interesting quantum effects. So what the property that I really want to point out here is this this phenomenon of Hilbert space fragmentation. This is actually something that people have often observed for quantum Fracton models. But we will see here that it's actually a bit of a challenge in order to stabilize some kind of quantum spin liquid phase. So of course there are also other sectors of the Hilbert space which have a larger density of flippable plaquettes. So the largest number that you can find actually realizes this staircase sort of arrangement, and in this case the plaquettes actually are overlapping. So in order to solve it, we need to resort to numerics. I'm choosing here green function Monte Carlo, which is a particular flavor of quantum Monte Carlo, and in this case we can study this this model, for instance, for mu equals 0, and in this case you see no sign of pinch points whatsoever, and instead we have ordering peaks that correspond to this staircase pattern. That's probably not very surprising, because for mu equals 0 the system likes to fluctuate around the state with many flippable plaquettes, which is this staircase here. However, something that is slightly surprising is that if you go to mu equals 1, your ground state forms an equal weight superposition of all the states in the sector, so that is still an exact result. However, you still see features of this long-range correlations, and I don't know how good it is to see here in the beamer, but there are red dots here in the middle at the same locations as before. And actually, this state here still realizes some kind of trivial dynamics, and the reason for this strange behavior is that the Hilbert space fragmentation that I showed you before. So essentially, what happens is that the Hilbert space breaks up into exponentially many sectors, but each of these sectors has some sort of trivial quantum dynamics, or at least trivial in the sense that no quantum spin liquid can be found. And then even at the Roxer-Kivelson point, where all of these sectors become degenerate, the best that you can realize in this kind of system would be, again, a classical spin liquid, because it does not feature any tunneling process between all of these configurations. So in order to solve this issue and to hopefully realize a quantum Fracton phase, we need to find a way to tackle this problem of Hilbert space fragmentation. And actually the solution is to go to higher spin degrees of freedom. And in this case, fragmentation is still there, but the sectors become larger. And in some of these sectors, you can then realize a quantum spin liquid. So before I show again numerical results, let's briefly discuss the phase diagram that we would expect to find for spin 1. So now this Hamiltonian is the same. The plaquette flip operator is the way that I've shown you before, but only the spin configurations can take up, down, and 0 states. And we can divide the phase diagram in 3 parts. One part is for mu greater than 1, and in this case, the Hamiltonian here is positive semi-definite, so you can minimize the energy by considering configurations which are annihilated by this plaquette flip operator, and this again leads to trivial quantum dynamics. Of course, there can still be many solutions that satisfy this, but at the most this will give you some classical description again. And then at mu equals 1, there will be a first order phase transition to this Roxer-Kivelson point, in which case there's this equal weight superposition of all the configurations. And now the question that we want to answer is there a finite regime between mu equals 1 and mu equals infinity where the system realizes some kind of quantum spin liquid phase? And finally, of course, we know that for mu equals to minus infinity, again, the term that dominates is this term that counts the number of flippable plaquettes. So here we have very little dynamics. The ground state sector actually will be a sector in which all the spins are in the 0 configuration. So in this case, you can flip every single plaquette in the system. And in this case, the system describes a trivial paramagnetic phase. Now, let's look again at this staircase sector, which surprisingly we also find to have the lowest energy from all the sectors that we've considered. And we can again look at the spin structure factor, and we find that for mu equals 0.8, there's still this ordering peak, which corresponds to this staircase arrangement here. However, if we increase mu to larger values, this peak disappears, and it gives rise to this interesting pattern of suppressed features here at the origin. And if we increase this RK potential even further, this kind of solution transforms smoothly into something that looks exactly, again, like the classical pinch point features from the Gaussian approximation, but now with the difference that this is all realized in a single sector of the Hilbert space. And I just briefly want to point out how different this looks from the spin 1/2 case that I showed you previously. And you can characterize the nature of this phase transition by now looking at the behavior of this spin structure factor as a function of mu, because the spin structure factor for all system sizes shows a very abrupt change at mu equals 0.8. So this is indeed a first order phase transition between an ordered phase and a disordered phase. However, even though it already looks a bit like it here, we still haven't really found out whether this is a quantum Fracton spin liquid. So in order to answer that question, we have to once again go to gauge theories. So just as in the case of quantum spin ice, you can write down an emergent gauge theory for this Hamiltonian, and the recipe to do that is shown here. You have an emergent vector potential, which you use to replace your spin plus and spin minus operators, and that allows you to define a magnetic field. And okay, skipping a lot of steps in between, we again can write down an approximate Hamiltonian, which is quadratic in E and in B. And this Hamiltonian now has exact solutions in terms of photon excitations, now with a quadratic dispersion as opposed to this linear dispersion that you'd normally expect in electrodynamics. You can also compute the spin structure factor from this gauge theory, or rather the electric field correlator, which becomes analogous. And once more, it is given by this product of the classical spin structure factor with this quadratic photon dispersion, and it leads to something that looks like this. And in particular, we see that this pinch point is now suppressed corresponding to this quadratic photon mode. To make a comparison, I also show you now a different sector, which actually has an even larger non-magnetic phase. And in this case, we find that for mu equals 0.8 or mu equals 0.4, this gauge theory actually agrees rather nicely already with the numerics that we find. And in order to make this analogy a bit more easy to see, we can also plot a path in momentum space along these high symmetry points. And in this case, the black dots correspond to the quantum Monte Carlo results, and the red lines correspond to the field theory expectation, or rather the fit, but we are only using two fitting parameters. So, and we see that for a large range of mu, okay, there's a lot of values in between that I'm not showing here, but up until mu equals 0.4, it agrees quite nicely. And then for lower values of mu, this description breaks down and the system realizes some very kind of complicated kind of order. However, in the regime where the order is not setting in, we actually do observe that the theory is described very well by emergent rank 2 quantum electrodynamics. And I want to briefly point out that, of course, all of this behavior that you see depends kind of strongly on the sector of the Hilbert space that you're looking into. So in particular, we find that low-lying energetic sectors all have this kind of behavior where they realize a liquid phase that can be described well by quantum electrodynamics. However, in highly excited sectors, for instance, you can always construct a sector with no flippable plaquettes. This will, of course, not be the case. So the dynamics really is governed by this sort of division between trivial sectors and sectors that can realize something non-trivial. So I can now summarize my main findings. I introduce you at first to these twofold pinch points, which are a signature of an emergent Gauss's law. And if you generalize this Gauss law to a higher rank, this will be indicated by fourfold pinch points in the structure factor, which correspond to classical fractons. And if you consider the quantum gauge theory of this, and you solve the Hamiltonian, you get gapless photon modes, and these photon modes lead to a suppression of these pinch points according to this dispersion. And I also introduced you to the spiderweb model, which is the simplest model that you can use to study these kinds of physics. And I considered two particular cases, spin 1/2 and spin 1, which actually show very different results, because for spin 1, the large degree of Hilbert space fragmentation prohibits the formation of a quantum spin liquid state, whereas for spin 1, a quantum spin liquid can be formed in low-lying energetic sectors of the Hilbert space, and in each of these sectors you get a gapless photon mode which emerges. So with this, I want to thank you for attention, and I invite you to ask questions.
Questions? I guess we can skip the microphone.
Mm-hmm. Thank you.